Bismillahirrahmanirrahim. So before starting the session, if you have any question from the last lectures. Okay, hopefully you are passing your time in a better way. So even we have some difficult time with our parents, with our relatives, and more. Definitely, this is a tough time going on. So I believe that this video lecture, we have uploaded the video lecture, and that will definitely help you. So the task, what you need to do, always go through the video lecture, and afterwards, please return your task so that you can at least go through the whole lecture. Because before the final, we have the before or after the final, so it will be scheduled accordingly. There will be viva session based on the syllabus after mid, and we need to also take one quiz, and that can be organized in the next week. The quiz syllabus will be the quiz we have already taken the few days back. From there to today's work. Okay, so that is the last topic we'll cover today will be the syllabus for the next quiz. The seers are requested to confirm me with the propose me some time and date for the quiz, so that we can conduct it in the next week, inshallah. Before that, if you have any question or comments, we can discuss. Okay, let me start the session with the group delay. So we have already talked about the group delay the last day, though we need some more explanation on this topic. This is very important for understanding the filter design, because you need all pass filter for all pass filter. We'll talk about all pass filter today. That is the main topic. However, before presenting the all pass filter, what is the purpose of the all pass filter? That is very important. In case of FIR filter, as we already know that the phase response of a filter is always linear. That means it is proportional. The phase response is directly proportional to omega. And from there, we can also find that for the linear phase, this is the concept, the linear phase, let's say that is a minus omega into 2, or you can say minus 2 omega. That is, of course, a linear phase response where omega is increasing, the phase value will also increase like that. In that case, the group delay is nothing but the rate of change of your phase with respect to omega and negative of that. So it means that we have minus d by d omega, and what is the angle phase rate of change of the phase? That is 2 omega, and that will give us the value 2. So this is the group delay. So what does it mean by the group delay? So how much delay you need to reconstruct your original signal? So how much delay you need to wait to reconstruct your original signal? So let me give you the example with a practical scenario. Okay, so side by side, what I want to mention here. So let's say we are talking about a FIR filter where the phase response is linear. So that is linear. In case of linear phase response, how it looks like, okay, the plot is like this, where this is omega and this is the phase value. Okay, the phase is presented here with the value of negative number, of course, with a negative number. Now, what about the group delay? In this case, the group delay can be represented as the tau omega, and which is a constant value. For example, if this is equals to minus 2 omega, in that case, this is equals to 2. That means for all the frequency, the delay is 2. What does it mean in practical sense? That is the question. In practical sense, you have the input and you have the output. So this is your xn and this is your yn. In the frequency domain, we represent this as x omega, y omega. So this is our h omega, the filter we have already designed. And this is, of course, a FIR type filter. Now try to understand these two portions. Let's say we have a signal xn, and that has been made by 3 frequency component. So xn is equals to x1n plus x2n plus x3n, where x1n is 1 hertz, x2n is 2 hertz, and x3n is 3 hertz. So they have higher frequency, and those subscript numbers shows the frequencies. So I would like to draw those here in the left side with the same time scale. Okay, let me take some other color to represent this scale. Okay, first I'm drawing the x1n. Let's say this is x1n, and if this is x1n, then of course this is x to n, and have 3 hertz within that space. So that means 1, 2, and 3. So you need to understand each and every portion, and if you have any confusion, just let me know that. So this is our x1n. Make it more clear. So this is our x1n. This is x2n, and this is x3n. Okay. Of course, when this signal and combinedly these 3 signals makes our xn. Whenever it is passing through this filter, they have made some delay, and that's why this phase delay concept can be represented here. Okay. For example, here this is the line for x1n, the frequency, and this is the line for x2n, and this is the line for x3n. Because as you know that these points are for different frequency, and since they are these x1n, x2n, and x3n, they are different for different frequencies. So that's why that can be presented here. We are just mentioning where they are. So they are presenting different frequencies. From the phase response, what we can find that definitely the x1n should have some phase delay. Phase delay, it will make some delay. So let me draw it in the right side. So we are talking about the output. So these are the outputs. Okay. So the whole signal, the x1n, would be delayed with some phase. What is the phase value? Okay, let's say the phase value according to the diagram, you will find what is the phase value. So this is theta 1. Theta 1 is the phase delay. So if I put a line over here, I need to make a delay of what? This is theta 1 or phi 1. So that is the delay according to the phase response. And now I can draw the diagram in the similar fashion. Okay, so now you can say that, okay, this is our x1n. It is passed through the filter. However, it makes some delay of phi1. What this phi1 represents? It represents the phase of x1n. That is very significant. Okay. Now let me just give you let me draw the line extended version of this one, and now the second one means the x to n. I'm drawing x to n. Okay, x3n as well. Okay, now you probably ask me that why they have the same phase delay, even though it has been reported that they have the different phase delay in the phase response. Try to understand that in this respect, in case of x1n, what is the phase delay? That is phi1 with respect to x1n. How much degree it actually been delayed? What is the phase of that? And in case of x to n, the distance is the same. What about the phase? Is that higher or it should be lower? The same amount of distance will carry high amount of phase or lower amount of phase of x to n. Any of you would answer? For example, if I just put this line, let's say I'm putting this line arbitrarily, this line in between, if I talk that in between, what is the phase for x1n? What is the phase for x to n? Definitely the phase is higher. What is the phase of x3n? Definitely that is more higher than x1n and x2n. You got my point? Let's say for x1n, if I draw here the line, and if I draw here a line, in that case, it elapses half of the phase. Here it elapses full cycle of the phase. Full cycle means what? Full cycle means twice pi. Half cycle means pi for x1n. And for the third signal, that is thrice pi, because this is twice pi for third signal, and this is pi. So that is thrice pi. So what we can understand, the distance looks like the same in the time scale, but what about the phase for different signals? For signal number 1, that is only pi. For signal number 2, this is twice pi. For signal number 3, that is altogether thrice pi. So similarly, what is the, if we make the delay for the first signal is, for example, make it like this. If the delay is pi here, so what is the distance delay for the x to n? That is twice pi. And for what is the delay for x3? That is thrice pi. So here, what we can mention in the left side, this is basically pi. This is twice pi. This is thrice pi. Just for give you the understanding. So this is for omega 1. This is for omega 2 from signal number x2, and this is for omega 3. We have this kind of phase delay. Probably you can understand the whole scenario here. Any confusion? You should understand each and every part here. Okay. If you have any confusion, just let me know. Okay. So now the thing is very interesting more that you find that in the time domain, let's say the time domain, these are the three pulses. These are the three pulse positions. Okay, three sample position. So from the time domain point of view, they have delayed for how many samples? This is sample number 1 and this is sample number 2. So what is the delay for x1n? What is the delay for x1n? That is 2 samples. 2 samples. What is the delay for x2n? Please answer. What is the delay for x2n? How many samples? Are you listening? What is the delay for x to n in the time domain? How many samples?
So 2.
2 samples. What is the delay for x3n? What is the delay for x3n? What is the delay? I shouldn't proceed without getting your answer. I'm asking what is the delay for x3n? How many samples?
It's a 3, sir.
3 or 2 samples?
So
3.
2 maybe.
It must be 2 samples. From the time domain, it is very clear that for the x1n, that is 2 samples. For x2n, that is 2 samples. And for x3n, that is 2 samples. Physically, those are the 2 samples. So that means whenever this phase response is linear, that means that after a certain period of time, I'm mentioning a certain period of time, all the signals are in the same phase. All the signals are in their original phase. So this is the original phase. So these three makes your xn. So whenever you want to retrieve your original signal back, so how many samples you need to wait in the output? How many samples you need to wait? Whenever you are getting your output yn, first 2 samples, first 0th sample and the first sample, you don't need to care. You need to start with the second sample. So after 2 samples, you can collect the value. You can take this value, and reconstruct your signal, and you can reconstruct your signal back. And this is the whole scenario of the linear phase response. Is it fine? Do you have any question here? No question. Yeah, 48.
No, sir.
Okay, because this is very important. Whenever we'll talk about, okay, this is a linear phase, what does it mean? It's linear phase means the group delay is constant. What does it mean by the group delay? I believe that you have heard about this group delay in your communication engineering, maybe in your signal and system or somewhere else, but I'm not sure about this, whether you understand physically what does it mean by the group delay. And this is the group delay. It looks like we have the difference between different frequency component from the phase response point of view, However, in case of group delay, we can find that this is a constant. What does it mean by the constant group delay? And this is the meaning of the constant group delay. Okay. So then what would be the final scenario, how it looks like in practice? Let me give you the example with this. Let's say we have a signal. Maybe I can make it more visible. We have the signal xn, where that is a sine 0.2 pi n, sine 0.4 pi n, and sine 0.6 pi n. I believe that you can draw it in proper time scale. So of course, this frequency is lower than this second one, and the third one is the highest frequency carried signal, and all together they makes our xn. Okay, now with this is an LTI system. We are passing our input to the output. Any LTI system is definitely works like a filter, and for this LTI system, let's say this is our group delay. What is the group delay? The group delay looks like 300 samples. Group delay is 300 samples. What does it mean? It means that this 0.2 pi frequency will make the delay of 300 sample. 0.4 pi signal will make a delay of 300 samples, and 0.6 pi that will also make delay of 300 samples. So all the signals will make 300 samples delay. The phase response is not mentioned here, but since the group delay is a constant value, we can ensure that the phase response is of course a linear one. From there we can say that this LTI system is a FIR LTI system, so FIR type filter. Okay, now with a graphical representation we can show it. Let's say our signal, this is our xn, this is our xn. So where xn is such that first we have this is the frequency of 0.2 pi. This is the signal of 0.4 pi, and this is the signal of 0.6 pi. Altogether they are xn, but they are separated. So the signals, the x1n, this is x1n, then we have some time delay, and then we are sending x2n, and then we have some time delay, and then we are sending x3n. Okay, now it starts, the xn starts with the with the sample number 0. So in the output, what should be the starting point of that signal? Of course, that experience 300 samples delay. So it will start with 300, and that's for sure. And after that, the signal will propagate like this. Now comes to the second one. What is the frequency of this one? The 0.4 pi. If that is 0.4 pi, how many samples it will be delayed by this LTI system? Of course, we know that that will be 300 samples delay. So if you can target that these samples start at 100 time cycle. So 100 plus 300. So what would be the starting point? That should be 400. And in the last case, for the last signal, what is the starting point? The starting point, it start at 200 samples. So 200 plus 300, so it will start at 500. And as we can see that it start with the 500, and after that we have. So exactly what we can try to understand, that we have our xn and we got our xn back just after 300 samples. So we need to wait for 300 samples, and then we need to accumulate all the things, and it will generate our original signal. Okay, so this is the main idea. Okay, any confusion here? No. Okay, very good. Then this is an example of nonlinear phase. Okay, so first of all, we just representing the group delay. So let's say for 0.25 pi, the group delay is 300. Okay, so for this frequency, the group delay is 300. For 0.4 pi, the group delay is 200. And for 0.6 pi, the group delay is 100. So how the phase response should be looks like. Let me draw it, the approximate phase response. Maybe you need to draw it in your viva or in your final exam. So the group delay is given, how the phase response looks like. As you can see that for the low frequency, the group delay is higher. So the rate of change should be higher. In the second one, the rate of change should be average, like this. And for the third one, the rate of change is very low, like this. Now you can see that there are 3 points, so 3 sections, 1 section, 2 section, and 3 sections. Maybe this is mentioned as 0.2 pi. Maybe this is mentioned as 0.4 pi, and this is mentioned as 0.6 pi. So this is with respect to the angle of your filter, and this is your omega. So everything should be very clear. So in this band, for the first band, you can say, what is the rate of change? The rate of change is 300. If the rate of change is 300, that mentioned that we have 300 sample delay in that case. In the second phase, the rate of change is 200. So the sample unit, the signals, these signals will be delayed by 200 samples. For 0.6 pi, the signals will be delayed for 100 samples. Let me show the output for a practical case. So again, we have the same signal which we have previously. If we want to draw the frequency spectrum of xn, we got this kind of 3 stem. One is for 0.02, one 0.04, and another for 0.06. Okay. Now, this is the portion we can draw today. With your help, we can draw it. So the first one, this is the signal frequency is 0.2 pi. It starts with 0. After passing through this, where it will start? Where that will start? From the group delay point of view, where it will start.
So from 100.
What is the delay for 0.2 pi signal?
300.
300, yes. So this signal will be delayed for 300, and after that it will start. So then what will happen? It will start with, let's say this is 100, this is 200. Okay, let me make it more concise. 100, 200, and this is 300. So at 300, this is 300, our signal, the black signal, the high frequency signal will start and ends. Okay, fine. What about this one, the second one?
200.
Yes. So it start with 100. It start with 100. And what is the delay for 0.4 pi? What is the delay for that? The delay is 200. We have already mentioned that in the group delay, it delayed by 200, and it start with 100. So what is the starting point of this second signal? What is the starting point of that? Actually, it start with 100 and delayed for 200. So that means it will start with at 300 sample. So that means the second signal will start with 300 sample like this. So that is the second sample. Is that clear?
Yes, sir.
Okay. For the third one, it start at 200, and for 0.6 pi, what is the delay? It
100.
observed 100 delay. So now it start with 200 and 100 delay it will observe. So altogether this is 300. So again it will start with the same point, but since this is a higher frequency component, so this is a higher frequency component. Now the question is, how can you retrieve your original signal? Is it possible? That means now is it your XN? Is it your XN?
No, sir.
So this is very difficult. Now your signal is passing through a LTI system, but unfortunately due to this different sort of delay of different frequency component, you are getting something which is not your original signal, and that's why there are some distortion, and this is called phase distortion. This is called phase distortion. Phase distortion, very important. What is phase distortion? Due to the change of the phase, shifting of the phase, due to the non-linearity of the filter, your signal might not been retrieved properly, and there are some noise, and this noise is known as the distortion, and this distortion is known as phase distortion. And this kind of filter, as I already mentioned here, this kind of filter, like where the group delay looks like this, and from the phase delay point of view, it is a non-linear in nature. If that is like this, you can understand that this is a IIR type filter. That is a non-linear phase, and this non-linearity makes your life very difficult, as we have already mentioned it in this example. So it makes your life difficult. What is the solution? That is the main point or focal point. So that means you have a IIR system and the output is questionable, because that makes our life difficult. What the people can do, they can design a all-pass filter in such a way so that this combination of IIR and all-pass filter works like an FIR type filter. That is the idea. So that means you have your xn, you want to get your yn is equals to xn after, let's say, after 300 samples, and that makes your life easy. So how you can design this all pass filter? The concept is, again, you have your IIR filter, okay, that has some advantage. We already know that. But however, there is a disadvantage of non-linearity of the phase response. If there is a non-linear phase response, we have some problem in the output. To tackle that problem, we can design an all-pass filter. This all-pass filter is also one kind of IIR filter, which makes our overall filter as a FIR filter. And that is the purpose of all-pass filter. From the phase response point of view, I can give you one example. Let's say what we have shown it in the previous section. Let's say this is a phase response, this is a phase response, and this is a phase response. Okay, we have three sections. If you can look at, we have three sections. This is linear or non-linear. Of course, this is non-linear. Now I am designing an IIR filter. In the first section, if you can look at, in the first section, the rate of change is very high. And in the last section, we have the rate of change is very lower. Let's say our target is to make a linear phase response. So that is our target. So what I can do for the first section, we can take lower phase response, very lower phase response. For the second section, we can take it like as it is. Okay, let me section out first of all in the three sections. So for the first one, definitely we need a very low rate of change. For the second one, whatever the change there, we can align with that. And for the third one, we can get higher rate of change. We can get higher rate of change. So when definitely you can understand, we are doing the opposite of what we have done here. We have done the things, and this is for conventional IIR type filter, and this is for all pass filter. As we can understand, in case of IIR type filter, we get the output. That is exactly okay. No problem with the output, but the problem is the phase response. That's why we are designing a all pass filter. All pass, what does the all pass do? That will actually pass everything, but we want to control the phase of the IIR filter, and that is the purpose. It will pass, this all pass will pass all the signals. So all the signals it will be passed through. However, it can control the phase, and that is the most significant part of this kind of filter. And this is how we can control our overall signal processing. Whenever we need to design, we need to take the advantage from the IIR type filter. Any confusion at this moment? Now in the next step, we will design our all pass filter. Definitely you can't design exact tuning of the all pass filter. There are some problems, trial and errors. However, you can check it. You can design very close to the expected value. Okay. Please do not count this. I have already shared this PDF file, or whenever I will share that, do not take it as an example. So the example I have shown it in the white paper already. You can take it as the phase response curve for the IIR filter and for the all pass filter. Okay. Okay. Now we can move to the all pass filter. How we can start designing the all pass filter. That is the portions we'll talk about. Of course, all the all pass filter is an IIR type filter. No doubt about that. No doubt about that, because there the phase response is also non-linear. Okay, so we start step by step. Let the transfer function for all pass filter is AZ, where A is for the all pass filter, and the normalized function is this. This can be also mentioned as the inverse function. This can be also mentioned as inverse function. What is the inverse function? Let's say if you have a function hz and you have the inverse function. So what is hz? Let's say it looks like a low pass filter. Now h inverse function, it looks like, obviously it looks like a high pass filter. Then if you multiply this to hz and hz minus 1, what would be the output? Of course, that will give you in the frequency domain, it will pass everything. From 0 to pi, it will pass everything. From 0 to pi and 0 to pi. So in the first filter, it pass something, block something. In the second filter, it blocks something, it pass something. Whenever you multiply these two together, definitely it will pass everything. And this is known as the inverse. This is known as the inverse filter. So whenever you multiplied your filter transfer function with the inverse filter transfer function, of course, the output should be 1. That is the definition of the inverse filter. So sometimes we need this inverse filter part as well. We can design it very easily. If you have this, you can design it from your Z domain representation. Okay. From there, we can also find that what is the magnitude response, the power spectrum of the all pass filter, because A is representing the all pass filter. The thing is very simple here. That means everywhere the magnitude is equals to 1. Now the question is, what about the phase of that all pass filter? That is the question, and I have written that anything. So you can control the phase response by choosing the pole and 0 of the all pass filter, and that is the most interesting part of the all pass filter, and that is the purpose of the all pass filter. What is the purpose of the all pass filter? It will pass everything, but you can tune or you can fabricate the phase of that filter so that a IIR filter, then a all pass filter can works like a FIR type filter. That is our purpose. So a all pass filter is one kind of IIR type filter because it produces a nonlinear phase. Okay, So from the pole zero point of view, what we can write, the transfer function of all pass filter is equals to PNZ over QNZ. Like this, the HZ, the transfer function, can be written as YZ divided by XZ. That is the simple concept we know. So any transfer function can be represented by the zero locations and the pole locations, the concept of like this. Similarly, this is the inverse transfer function, or inverse function can be represented by this. And this is very simple, because whenever you are switching over the pole locations and the zero location, it will actually help you to design the opposite type of filter. For example, if you have the filter, let's say this is the unit circle, and you have here the zero, and you have the pole here. What kind of filter is this? Any of you? What kind of filter is this? Low pass or high pass?
Low pass.
This is a low pass filter. Now, if we can change the position of the zero inverse in the inverse means if that was in -1, now it is in 1. So if we change it there, and since the pole at the zero means if you change it, it will be remain at 0. Of course, this represent high pass filter. Now, if this is your AZ, this is not the AZ. So let me write in this. If this is your HZ, then this is your HZ minus 1. So that is the inverse of that. Okay, so that is how you can change the position of the pole location and the zero location, and you can design another filter. Okay, whatever the case, what we can do, then we can multiply these two, and we already know that after multiplying we got this output 1, and this part is this one, and this part is this one. So that's why we can write it like this. This is very important formula here. We have found that the PNZ, the pole, P represent the pole, the inverse poles is equals to zeros, and the inverse zeros, the multiplication. We made a question that how to do that. Okay, so how we can build this? Okay, that is the question, and we'll solve that in the subsequent section. Let's take a first order all pass filter. So this is an example by which we can understand the process. Let's AZ is equals to this. This is of course a first order filter. This is of course a first order filter where K, previously we make A, now I am giving K. Okay, so no problem with that. So AZ is equals to K 1 plus AZ to the power minus 1 over 1 plus B Z to the power minus 1, where of course B is less than 1 for stability. You understand that this B represent the pole location, and this A represent the zero location. So 0 can be anywhere, but the pole should be inside the unit circle for a causal system, causal stable system. So for the stability, we always think that our system is a causal system. In that case, for stability, B should be less than 1. Okay, so this is I believe that you don't have any confusion that this is a first order filter. So this is a first order filter, and from there, okay, we just replace the value of Z with Z to the e to the power minus j omega, letting that R is equals to 1. From there, you can elaborate the things trigonometrically by putting the Euler's formula. We can have this equation, and from there we can go for the magnitude response, because our main target is to the magnitude as well as to the phase. So the power spectrum can be written like this. and it can be rearranged with this value. Okay, now what would be the output? Of course, this output should be 1. This is not a one-to-one function, so it can be, you can choose different value for making it 1. Okay, so for example, if we take a is equals to k is equals to 1, let k is equals to 1. So let's say k is equals to 1 and a is equals to b. In that case, of course, this is equals to 1, and you will find that. Okay, so I am making that. So this is equals to 1 and a is equals to b. So b is replaced by a everywhere. So you can find that this is, of course, is equals to 1. Very simple. But the problem is, in that case, this also shown that, try to understand that k is equals to 1 and a is equals to b. What is this? This is your power spectrum. But what about AZ? We need to find it out. So where is that equation? Try to find that this is your equation. If you put the value k is equals to 1, k is equals to 1, and a is equals to b, in that case, what will happen? This is equals to 1, exactly 1. So the magnitude, what is the magnitude? AZ. The magnitude equals to 1. What about the phase? The phase is also constant. You find that the phase is 0. I'm not sure about this. So by letting k is equals to 1 and a is equals to b, what you are finding? You are finding that the a, z, let's say the power spectrum, that is equals to 1. We are happy with that. Whenever we took the value az, that is the transfer function of the all-pass filter, we found that this is equals to 1 and this is equals to, again, this is equals to 1. So altogether it gives 1, and there is no imaginary part. The imaginary part is equals to J0. That means it has the magnitude 1, but it has the linear phase. There is no non-linearity of the phase over there. So you don't have the phase quantity here. You can't control your phase. You can have only the magnitude 1 for all the frequency. That is good. But what about the phase? Can you control the phase? If AZ is equals to 1, can you control the phase? No. The answer is no. So that's why we shouldn't go with this value. K is equals to 1 and A is equals to B. That will give us this. We are happy with that. But unfortunately, you can't control the phase with this. What is the second choice? The second choice is, if we choose A is equals to 1 by B and K is equals to B for this value again, so choose it, we can also find this is equals to 1. Just put it there and you will find. So let's change it. So this is B square and A is equals to 1 by B. So that's why this is B square. A is equals to 1 by B and A is equals to 1 by B. So this will give 1 by B and this will give B and the value. So then you can find that, of course, these numerators and the denominators will cancel each other and that value is equals to 1. On the other hand, what will happen? This is the interesting part. If you look at the AZ, putting that value, the transfer function of the all-pass filter, put the value A is equals to 1 by B and K is equals to B, you are getting ultimately this result. And now we are very happy because, of course, the magnitude response is equals to the power spectrum is 1. We are happy with that. And what about this? We are getting different phase. We can control the phase of the filter. Now you can control it. Now you can see that shows that the magnitude is 1 any value for omega. Of course, the magnitude is equals to 1 for this filter. You can write it like this. This is 1 plus b by z, and this is b plus 1 by z. So here it is actually, this is bz plus 1 divided by z plus b. So for this, we definitely got the magnitude response is equals to 1. However, what about the phase? You can control the phase by based on the value of the b. You can change the position of the b, and you can control the phase of that all-pass filter. So this is the fundamental equation. From the fundamental equation point of view, so we have already derived this, and we know that we can express it like that. Again, az can be written like that. How? With respect to qz, I have already mentioned here. For example, if this is a qz, 1 plus b z to the power minus 1, this is your qz. If I made it z to the power minus 1 into q z to the power minus 1, what is that? Z to the power minus 1, q z to the power minus 1. So 1 is there, plus b z to the power minus 1 is replaced by z, which is z to the power minus 1 plus b, and which is nothing but this is pz. So we can write that pz is equals to z to the power minus 1 into q z to the power minus 1. So in that way, we can write az is equals to this one. This is the note. Okay, don't confuse with this. This is for the first order. Now, if we look at for the nth order, what will happen? For the nth order, this 1 is replaced by the n, z to the power minus n, qn z to the power minus n, and qn z to the power z, qn in the bracket, the z. So it mentioned that it is very interesting that for the first order filter, even if you can design the pole location, from there you can also find where are the zero locations. You have the pole locations. From there you can also find where is the zero locations. This is the fantastic idea. Similarly, for the nth order filter, if you have the pole locations, you can also find where are the zero locations, and it can be elaborated like this. So the qn, first of all, the qn 1 plus d1 z to the power minus 1 plus d2 z to the power minus 2, and like this. And what is this part? Of course, what you need to do, this should be multiplied with z to the power minus n, and all the z to the power minus n minus 1 is replaced by plus 1. You need to replace that minus value with the is that, yes, so that will be replaced by the plus value first, and then you need to multiply it like this, and afterwards you'll get something like that. Probably there is a small mistake here. However, if you have this is the baseline, this is the fundamental, this is definitely, this is equals to qn z. Just multiply zn into qn z to the power minus 1, and then you can find whatever the polynomials you should find in the numerators. And you can find that this is known as this all-pass functions are also called the romantic function. Romantic means you have the couple of poles and the zeros. If you have the zeros with the vice versa, you have another poles. That's why this is called the romantic function. In practice, what happens, we'll talk about in the next class. If you have let's say you have the pole here at 0.5. Where is the 0? The 0 is at 1 divided by 0.5. That means at 2. So at the location of 2, you have the 0. If you have a 0 here, if you have a 0 here at some location, definitely you should have another pole here. So that's why these are called the romantic functions. So we have the couple of poles and zeros with a vice versa relation. On the other hand, if we have, so in the next class, I'll talk detail about this. If you have the 0 is here, very close to 1, let's say 0.9. Where is the pole location? That is at the location 0.1 divided by 0.9. 1 divided by 0.9, that means a little bit outside of the circle. So that makes a pair of the poles and zeros. So that is the phenomena of a all pass filter. Okay. Okay, there are very small part of this, so I do not want to extend that part today, because I believe that this is extensive lecture for today's class, for the starting part after a after one week break. Okay, so from these sections we can start our topic in the next day, inshallah. And this is the portion we have to consider for our quiz in the next week. The specific time and the date will be circulated through the Google Classroom, inshallah. Do you have any question at this moment on today's lecture, especially? Okay, it seems that you don't have any questions, so then we can stop our recording for today. Thank you.